This video is going to address the relationship between the natural logarithm and the exponential function. Just as a brief introduction, the natural exponential function is used to model exponential growth when it is expressed as e to the x, this function right here, which equals 2.718 and change. That's all you really need to know about the exponential function, is that for any value of x that you choose, you'll be taking 2.718 and raising this number to whatever power you choose for x, and it models exponential growth. The inverse of this function e to the x is called the natural logarithm. It has the exact same properties of the standard logarithm function, only with a base e, and we'll talk about that on the next slide. It's written as ln of x, pronounced ln. The only difference here is that your base is going to be e, this number right here. So this slide just shows the relationship between the logarithm and the natural logarithm function, the difference between the standard and natural logarithm. So for a standard logarithm, we're looking at log base a of x equals y. And what that implies is that whatever your base is, that base raised to the y power should equal x. That's the relationship between logarithms and exponents as expressed over here. So transitioning from the standard logarithm to the natural logarithm, anytime you see this ln, all that means is that you're taking the log with base e. So your base is the exponential function. And what that means is that the same properties apply with the standard logarithm, that e raised to the y power will equal x. So these two functions are inverses of each other, and essentially all that means is that when you compose one with the other, they negate each other, or pretty much they disappear. So if you have an exponential function here, and it's raised to the natural log of something, this e and this ln cancel each other out, and all you're left with is just x. Whatever this is here, it could be a fraction, it could be a decimal, it could be an entire algebraic expression, but if you have e raised to the ln of anything, that anything is all that's going to be left over, because these two will cancel each other out. Same goes for if you compose the natural log with the exponential function. So if you have the natural log of e to the x, whatever your exponent is here, because the exponential function will always have some kind of exponent up here, will equal just x. So the ln and the e essentially cancel each other out. So whatever your power is of your exponential here is going to be all that you're left with at the end. And using the properties of logarithms, this line down here kind of shows how this is possible. So if you take the natural log of e to the x, and if you look back at the last slide, all that means is that we're taking the logarithm base e of e to the x. Anytime you have a base and the same thing here, those two just cancel each other out, and all you're left with is x. And that's just a regular property of regular logarithms. So this slide just shows all the substitutions I'm going to be using for the problem you guys were working on. I have no idea what any of this notation means. I'm just going to go through the algebraic manipulations and applying the natural log and exponential functions to show you how they cancel each other out in this problem. So the formula that we're working with is this one on the bottom here in pink. And the reason we're working with natural logs is because the question is asking us to solve for time. Now time is in the exponent of the exponential function. So at some point, to solve for this exponent, we have to get rid of this e. How do we get rid of the e? We take the natural log of it, and those two functions will cancel each other out. And we'll go through that on the next slide with the problem. Okay, so here's our equation. Now the first thing we need to do to isolate our t is to divide both sides of this equation by FGO, whatever that means. So we're going to divide both sides by FGO here, leaving us with Fi over FGO, which should look familiar, equals 1 minus e to the negative t over your time constant. Now on the last slide we said that Fi over FGO was 90% or 0.9. So we can substitute that in right here. So let's do that. So now we have 0.9 is equal to 1 minus e to the negative t over your time constraint. I just wanted to shrink that down quick to make some more room to work. So now we need to get our exponential function here all by itself. How do we do that? We subtract 1 from both sides, minus 1, and that leaves us with negative 0.01 is equal to negative e to the negative t over your time constraint. Now notice that we have a negative sign in front of both of these equations. So if we divide both of these by negative 1, essentially those negative signs are just going to disappear. So just rewriting this in the positive form, we have 0.01 is equal to e to the negative t over your time constraint. Now, we have our exponential function isolated. We need to solve for t in our exponent. This is the point where you apply the natural logarithm. The same way we've been dividing by one side by FGO, you divide the other side by FGO. When you subtract 1 from one side, you subtract 1 from the other side. Once we get to this step down here, we take the natural logarithm of both sides of the equation. So that's going to look like the natural log of 0.01, which is something we can evaluate using a calculator, is equal to the natural log of e to the negative t over your time constraint. This is where the two functions cancel each other out. So all we're left with on the right side of the equation is negative t over your time constraint. So I'll rewrite this up here. We have the natural log of 0.01 is equal to just what's left, negative t over your time constraint. We've isolated the variable that we're looking to solve for, which was t. Now all we have to do is multiply both sides by the time constraint, evaluate what the natural log of 0.01 is, and then we solve for t. So I just went back and substituted in 0.9615 for the time constraint, which I guess you guys calculated at an earlier point in the problem. And evaluating the natural log of 0.01, we get negative 2.303. Now, to get t by itself, all we have to do is multiply by whatever's in the denominator here. So multiplying both sides by 0.9615, we get negative 2.214 is equal to negative t. Now, we're solving for time, so this should be a red flag for everybody that your time here is negative. We can't have negative time. But the time here is also negative. So to get t positive, just like we did back over here, dividing out the negative, you do the same thing, leaving us with t is equal to 2.214. And that should be your final answer.